Welcome to the Digital Amateur Television Experimenters Night. This is VK7OTC, the club station of the Radio and Electronics Association of Southern Tasmania. Amateur radio is a worldwide hobby that has many different aspects. Digital television is just one of the many modes and areas that are covered. Maybe you're interested in becoming involved in the DATV Experimenters Nights. You realise that you do not have to be a radio amateur or need any ATV equipment to participate anywhere in the world. Also participate in the night by coming up to the Queen's Domain club rooms. Yes, right on top of the Queen's Domain in the heritage-listed Coast Wireless Station. You never know, we might get you in front of the camera or behind doing one of the many roles during the night. We get underway with our program on a Wednesday night from 7:30 p.m. local time. We'll see you soon. This is VK7 OTC.
Okay, this is VK7 OTC, the club station of the Radio and Electronics Association of Southern Tasmania with our DATV Experimenters Night. And yeah, bit of a rough transition, that one. But anyway, we've got a huge night tonight. I'm not quite sure we'll get through all of it, but anyway, we're starting off, and I'm listening on Repeater 2 and also taking a look at the YouTube streaming chat channel, so you can drop a comment or a question or something into that particular channel. And hello Ben, and thank you for the confirmation of no echo. Yes, we are learning more about Open Broadcast Studio, and that was the source of our echo. And the source of our echo was basically the the delay between the input and output of Open Broadcast Studios, because we actually had both input and output being output to the stream. So it wasn't a problem on the RF channel, but was a bit of a problem on the streaming channel. So we've fixed that. Thank you, and thank you for the confirmation. So we're going to start off today with a little bit of a blast from the past. Oh, thank you very much, Ben. There you go. There's Ben watching it from home. So now, one of the things we will actually also be keeping a bit of an eye on is oh, there it goes. Our of course tonight is a blood moon. I'm going well tonight, aren't I? It of course is a blood moon, and in about an hour or two's time, the moon is actually the closest it's going to be to Earth for a little while, and it coincides with a blood moon. So we've got a bit of an OB set up outside. And I'll keep my eye on it because the clouds are going over. If we have a look at it right at the moment, we'll see that there's absolutely nothing because it's total cloud cover. But anyway, we'll keep our eye on that and see how we go. But we'll start off with a bit of a blast from the past, and I'll go to our close-up camera here. VK7AJ, Andrew Johns. Some of you will know Andrew. AJ actually asked me whether there was any use for a couple of books that he had, and this particular book, I went, yes, this is definitely has a use, and I would love to have a copy of it. Back in 1982, this was released by Dick Smith, and it was Dick Smith's Australian Amateur Radio Handbook. And it's absolutely fascinating to have a bit of a look through. I'll just go through a few of the pages. Probably slightly non-PC right at the moment, but the caption on this one is, "This YL must have won the lottery. Her shack has got the lot, including a mint computer and visual display unit over here." So there's some wonderful pictures and information in here from there's I think that might be a Creed Model 10 radio teletype. My old man had a few of those, which was interesting. But it covers all the different aspects: types of communication, licensing requirements, man-made aids for radio communication, what makes the Radio Shack tick, getting started on the airwaves, how to use the different amateur bands, home brewing antennas, accessories for the shack, how to solve interference problems. Well, there you go. See, we still had interference problems back in 1980. Operating procedures for exploring the airwaves, popular amateur activities, amateur radio clubs and shortwave listening, and then a whole lot of reference material at the end. So absolutely fantastic book put out by Dick Smith. Now, I specifically brought along today's copy, which is, and do a bit of a promo for Peter Parker, VK3YE, who has recently come out with the Australian Ham Handbook, with a foreword by the Right Honourable Mr. Dick Smith. So, and this is my signed copy. So, and very similar structure. So, and this is available at JCar or online for I think it's around about $30. I think from memory, but very similar idea, and quite a few years, 30 to 40 years apart. So there you go. Now, sticking with a Dick Smith theme. So if we stick with a Dick Smith theme, we'll just now. What we'll do, I'll just keep an eye on what's going on outside. No, that's all right. We still don't have a moon. It's still behind the clouds. But now, sticking with our Dick Smith theme, I happen to be down at the Barretta Resource Tip Shop. And shout out to Warren, who I think's next door in the club rooms. Went down and visited, and came across this. Jumped out at me on a shelf, 300 ohm flat ribbon, balanced TV cable, UV protected, 20 metres for indoor and outdoor use, black, and it's pretty much all there. So there might be a couple of metres taken off of it, so it's not quite 20 metres, but this is Dick Smith. And for the Princely Resource Tip Shop fund of $5. So I grabbed that because I thought I can certainly use that for my G5RV or for phasing lines on my Lindenblad antennas. So yeah, it's sticking with the Dick Smith theme. That's Dick Smith 300 ohm balance line from the Resource Tip Shop. So I thought that was a pretty good find. So I can definitely use it, and it's UV stable. It's the black stuff with multi-core. So there you go. There's a bit of a Dick Smith theme for tonight. Now, what we'll just do, I'll keep an eye on. No, we're still in the dark. So they're still behind a cloud. So we'll keep in on checking in on that particular thing. Now, the other resource tip shop. Now, people know that my one of my favourite stores is the Resource Tip Shop. I came across this box, and it has Hazel Brothers and a code on the front and a Spectra Precision AL24A box. And I thought, this looks like an interesting box. So I opened it up to find that there is a Spectra Precision, which is a Trimble company, auto level, AL24A auto level, complete with instructions. So this is an auto level, goes on a surveyor's tripod, but it had stickers all over it that said "Do not use, do not use." It had "Do not use" all over the box. Oh, hang on, we've got a bit of a and it's gone back behind the clouds. Okay. Now, if Warren's out there and you're listening, Warren, can you come into the studio, please? But do not use, do not use. And I couldn't, in the shop, I couldn't quite work out why you couldn't use it. You can certainly, the optics in it seemed okay. There's certainly the adjustment for your eye. There is the adjustment and focus was certainly still working, and also the azimuth arrangement, the fine azimuth arrangement on the scale was working. But then I realised that one of the three adjustments to get it level, there's a little bubble level here that you centre. There's a little bit of mirrored plastic here, so you can look where your eye is and make sure that you're in the centre, so everything is level. When I started playing with these, there were two of them that, one of which was not bad. It was a little bit bent, but the other one was well and truly bent and it was quite hard to actually get it out. And when I pulled it apart, it had well and truly, the brass bronze arrangement had well and truly been bent. I suspect it had fallen over and hit and bent one of these adjusters. So I thought, okay, I can do some work here. And so I undid it and tried to rebend it, and it broke. And I thought, okay. Machined up another one, so the equivalent, because I had the bent broken one, and oh, hang on, we're about to, and I'll just go and focus the camera. There you go. Oh, our blood moon's just disappeared again. Okay, I'll keep an eye on that. But I machined up another one and epoxied it into the existing knurled plastic nut so that it's equivalent, and we're back in business. All of these now work. And I've tried it on a surveyor's tripod. It works very nicely. So for the princely sum of about $60, I've actually got a auto level ex Hazel Brothers that has been put back into service, and it comes in a very nice a case with the foam all around it, so that it can stand. And it also still has all of the little Allen keys and all of the little adjusters. So the only thing that's missing out of this case is the plumb bob, which there is a little slot here. The plumb bob's actually gone. The plumb bob's for the centre of the tripod, to make sure that the tripod's actually upright. So I can machine one of those up. But anyway, that's the Spectra Precision auto level. So there you go. And there it is. So we got a bit of a progress on the blood moon. Oh, and we're going back into cloud. Okay, so I can feel this is going to be quite a disjointed night tonight. A little bit of night. And hello Harry and hello Xavier. I spoke to Xavier earlier. Happy blood moon night, Justin. Yes, thank you. Well, here we go. We're back again for a moment there. Oh yeah, not bad. We get a decent look at it there before it goes back into the clouds. So that's the actual eclipse starts I think in about an hour's time, and then it's about 2 hours until we get underway. So anyway, that's our blood moon and a little bit of resource tip shoppery. Now, okay, our next bit, I just wanted to remind people and let people know. Oh, hang on, there we go. Let people know that during the week, the last couple of days, there was a general availability release of WSJT-X version 2.4.0. So this is the official general availability use, the GA release of 2.4.0, and the big difference with 2.4.0 is it has the digital mode Q65, and for those who don't know, Q65 designed for two-way QSOs over difficult propagation paths, including ionospheric scatter, troposcatter, rain scatter, EME, and other types of fast fading signals. So Q65 is now into WSJT GA release 2.4.0. So available on the on Joe Taylor's download site. So well and truly worth a look. Now, okay, we'll get into. I'll just take a quick look at the streaming channel. Okay. Now, we have the next workshop 3. So workshop 3 in GNU Radio. So just let me go to here, and then we'll put that as so that I can watch the moon. Now, okay, we are back into GNU Radio, and you're seeing exercise 2 on the screen right at the moment. Now, just a quick reminder, there is this is what I'm following. It is the Microwave Update 2019 GNU Radio Workshop Notebook. I am going to diverge from this towards the end of this particular workshop, because there's a few things I want to do just to give you a bit of an idea about how useful I and Q or quadrature signals actually are, and a demonstration of that. So I'll just diverge from the book a little bit towards the end, but oh, here we go. No, it's it's not focusing right at the moment. So what we're looking at, and a bit of a recap on the core concepts that we went through last week. So we've got sources and sinks. Now on the actual it helps if you're on the right screen. On the screen, this is exercise 2. We've got a signal source, which is where we can set a frequency. We've got a bit of a throttle. Now throttles are required where you have something that hasn't got an external clock. And in this particular case, we have a display, the QuickTime GUI frequency sync. So this is like an oscilloscope. It does not have its own clock. It relies on the internal clock. And so if we were to not have a throttle in there, this arrangement has the potential of just taking as much CPU resource as it can. So we put a throttle in there just to make sure that it doesn't take off. So we've got our frequency source, our throttle, and we have a frequency sink. So a sink is something that takes the output of this flow graph screen arrangement that you come up with, and then the source is something that introduces an actual signal. So the source samples into your flow graph, and the sink removes samples out of your flow graph, and that can be a sound card, it can be a frequency generator, it can be a network stream, a TCP or UDP stream, etc. Now there are then transformational blocks, and we'll go into those in a bit more, things like low pass filters, high pass, band pass, FM demodulators, delay blocks, etc, etc, and we're actually going to go through a low pass filter later tonight. Signal formats. Now you'll notice that we need the input and output to match types, and you'll see this is a blue one. If I go in here and go through the up and down buttons, you'll see the color of them changing, and when it's not matched to what it's going to, it becomes red. So it tells you, and here we go, it's blue and blue. Now if we want to know what the blue actually means, we can go up to help and types, and the blue is a complex float 32 number, and I'll go into that in a short while as to what that actually means. But you have to match the input and the output to the types, the particular types. If they're not matched, it will turn red. And also, if there is a problem and the block title inside a block actually goes red, then there's something else wrong as well. You will not be able to compile your flow graph until you've resolved that particular issue. Okay, let me just scroll down a bit here on to make sure that I'm not. And the complex and versus a real stream, I'll go into that in a sec. I've got a bit of a demo that I've come up with for how that actually helps you. Now, some more hints and tips that I've come across during the last week. Over here where all of your blocks are that you can select, if you click inside this area and go Control F, there is a little find function that pops up, and you can go in here and go signal. If I'm looking for, say, a signal source, and it then brings up all of the things that have got signal in them, and there's the signal source, so I can just grab that and drag that onto the flow graph, and there it is, and you're ready to use it. And you'll notice that the signal source here is red because it's not connected to anything. It's just sitting there out in limbo. Anyway, we'll get rid of that. So that Control F is really, really handy. Now, okay, this is slightly different exercise 2 than what I showed you last week, because there is another block that's appeared here, which is what we call a QuickTime GUI range. And what the range does is enable us to put a control of some sort into our whatever our output is. In this case it's the frequency sink, so it's the oscilloscope output. It enables us to vary the frequency of this particular signal source within the actual screen, the actual oscilloscope screen that we're going to be showing this frequency sink. The way you do that is, we'll just open up the properties of the signal source here, and you'll notice there's a few things in here which are all set. The waveform's a cosine. The frequency, now instead of the frequency being a number, it's actually the letter F. So what we've done is made it the variable F, and if we then look at the QuickTime GUI range, the ID of this range is, surprise surprise, a lowercase f. So we match the variables between this range and the signal source, and what this enables us to do is actually set up and you can see here there's some values here. It starts at 50, at default 50, starts at 0, and the stop, so the maximum that you can go to is 10,000, and then the step rate is at 1 hertz, so at 1 hertz at a time. So this gives you the ability to put a slider to control the frequency, and it can control anything. Now, and how do you know what it can control? These underlines in each of these here, so all of these other than the output type, given that they're all underlined, means that you can vary any of these in real time. So you can have a control. In this case we've got a control on the frequency, which is that variable f, but you could have a control on the amplitude, you could have a control on the offset, on the phase in radians, and we'll look at that in a sec, and or on the sample rate, or on the waveform. You could select different waveforms real time whilst you're looking at that oscillograph. And we'll show you, because we'll just run this, go up here and we'll go run. So it goes off, tells you a little bit about what it's doing down here, and it comes up with the oscilloscope. And the oscilloscope, we've set it to a frequency of 50 to start with, but you'll notice up here at the top of the block is this frequency slider, and I can grab that with the mouse and you can see the frequency slowly going up. We're up to 5 kilohertz, and we can go all the way up to the maximum of 10 kilohertz, which is what we've set up. Now it's interesting, as you go through here you can see there are all sorts of little artifacts appear along the frequency spectrum, and I have a feeling that these are, because some of these devices to be able to get these frequencies are not quite what they seem. You get some little sidebands, some little harmonics coming up here every so often. But if you get to a frequency that is a commonly commonly divided number, you suddenly see all of those artifacts disappear, which is fascinating. So anyway, but what I'm just demonstrating here is you can put in controls. These are little controls that you can add, use the variable, match the variable to the actual characteristic that you want to change, and you can put as many of these in as you like, and I'll show you an example of that in a sec. So that's exercise 2. So that was just a little exercise to show you how to put in some controls. Now I'll just take, I haven't seen the moon for a little while. I'll just, no questions. So okay. Now what I tried to do here, I did a little thing on why do you use quadrature characteristics and terminology, and why do you go to all of the trouble of getting an in-phase signal and a 90-degree shifted signal, so an I and a Q signal? Because if you look at any sort of software-defined radio, everything uses I and Q, and all I and Q is, and the reason they do that is, I and Q is a really nice mathematical way to define your frequency, your amplitude, and your phase with 2 numbers. And so I thought about, okay, how do we represent this? And I looked at a few YouTube tutorials, of which there's a couple that our RF viewers will see if they stick around later. And what I thought was, okay, why can't we actually use the actual tool to be able to try and show what the benefits of converting everything to an I and a Q signal gives us. So just a little bit of a recap here. I'll just go to the close-up camera. So you'll remember there is a notation, a complex notation that gives you they call it a polar diagram or a constellation diagram, where you've got your imaginary number of Q axis there, and you've got your real I number, so this is the cosine and then the sine, and then you've got out from the center is a certain amount which represents your amplitude, and then the angle between there and your I axis is the phase. So this represents in two numbers, which is your I and your Q number. It represents the frequency, the amplitude, and the phase. And this diagram enables us to be able to plot, if you like, those numbers. Now, what it also introduces is the fact that there is the concept that there is no concept of there being a positive or a negative frequency. You can have either of them because given this is an axis of it's positive on this, it's positive on this axis, and then it's negative here and negative here. What you've got is the ability to have a positive frequency, amplitude, and phase in this segment. The combination of the two, the negative here, and the combination of the two here. So there is this concept in I and Q that you can have negative frequency. So that's one thing you've sort of got to you have to come to grips with a little bit. So that's the way that you can actually diagrammatically represent those numbers. So now, what I thought was, okay, how do we show this in the actual GNU radio tool? So what I've done here is come up with two signal sources. One's a cosine source, one's a sine source, and I've put here those sliders for frequency, amplitude, and phase in radians, and frequency, amplitude, and phase for the other source. Added those two together, put in a throttle because there's no clock, there's no external clock limiting the amount that it can be used here, and it goes into what is another type of sync, which is a QuickTime GUI constellation sync. So let's run this, and I'll show you what it then comes up with. Now, whilst it's doing that, I'll just bear with me because I'll go and realign the camera. Okay, right behind a cloud, so I think I've moved it a little bit. So what we're looking at here is we've got phase of Q, phase of I, frequency of Q, frequency of I, and amplitude of Q and amplitude of I. So I can independently vary any of these for the I and the Q signal. So what I'm going to do, I'll just put the amplitude down a little bit here. And you can see what we're looking at here is we've got both frequencies are at 50 Hertz, and we've got the phase exactly the same. So what I'm going to do is change the phase so that one of them is at 90 degrees and one of them isn't. because I'm not convinced that I'm getting the cosine and the sine function out here. I haven't quite worked out whether I am or I aren't right at the moment. But anyway, so what I've organised for the phase is each one of these steps is 90 degrees. So that's 180 degrees, that's 135, that's 180, etc., etc. So, and then the frequency and the amplitude. Now, this effectively represents a amplitude modulated signal, because what we're doing, if this was going up and down as an amplitude, as your voice or a frequency, then what you would be seeing here is an amplitude modulated frequency of this circle varying in diameter. You can see we've turned the amplitude down to 0, and it's disappeared because it's right in the center of the circle. Now this is now just bear with me, because I just want to change the auto scale to no here, because then I can show you what happens when you change the amplitude. We'll just recompile that, which it's doing right at the moment. Okay, so that 0, that's 90 degrees. Let's go. Now, okay. What we're looking at here. No, okay, no. Now just let me switch that auto scaling back on again, because I'll explain it a slightly different way. Okay, let's recompile. So when you, for a amplitude modulated signal, let's go to there. Okay, so as the amplitude is going up and down, that circle would be varying in diameter. Now, unfortunately, what's happening here is it's auto scaling as I'm changing it so that it is always that size, but it would be going up and down very similar to let me just get up on the screen. Let me just get up on the screen. This one, and I'll post this particular presentation in the text for the video. Now, this is actually AM modulation in I and Q. So what we're looking at here, we are looking at the Q axis here and the I axis here. Now, right in the center here, literally going in and out of that chart, is time. So if we were to represent that as time, so we've got our I and our Q axis, and we've got time along here. As the amplitude modulation varied from high to low to high to low to high to low throughout time, that's what it would look like on an I and Q chart, like we've got here. So, and if we then made that an X and Y axis, that's our more traditional AM type of signal. You see the carrier, which is the one that's varying. It is usually a higher frequency, and you can see that because each wave is closer together. Then that's modulated by a lower frequency signal, and you can see that's the lower frequency signal that it's modulated with. And if we then represent that in an I and a Q chart, that's what it actually looks like, looking down that time axis. So now, if we then look at something like frequency modulation in INQ, what that would look like is in 2D it would just look like a circle, very much like amplitude modulation. However, if we then put that on a time axis, you'll notice this bit of it is much higher frequency, and then with less of your audio frequency coming in, it's a much lower frequency, or it's a slightly lower frequency, and then it goes back up to a higher frequency. So on an INQ chart, a 2D chart like this, you don't get much in the way of AM and FM, because it's very hard to represent that that time axis. And if we then do that on a 2D graph, which is the one that we are much more familiar with, you find when the amplitude of your voice is much higher, then the frequency goes up. When it comes down in amplitude, then it goes lower in frequency. So this is the deviation they talk about in frequency modulation. So that's on the 2D. That's on a 3D on a time axis. Now, if we then talk about something like binary shift keying, binary phase shift keying, that it looks like on a 2D chart, you've got a particular phase, and then the phase changes. You can see here there is a skip, and it changes to 180 degrees in the other phase. So this is binary phase shift keying, BPSK, in 2D. On an IQ chart, again, it just looks like a circle. However, if you then plot that over time, you'll see its particular phase here, the phase changes 180 degrees at this point here, and then it's 180 degrees out of phase. So that's 2 bits. That's your 0 and your 1, or 1 and 0, or however you want to represent it. So that's BPSK. Quadrature phase shift keying, etc., etc. The quadrature phase shift keying, you've got 4 quadrants here, because your Q axis is here, your I axis is here, times through the middle. And if I start changing the phase here, you'll notice that there is all sorts. So change the phase, change the frequency. There are all sorts of varying the frequency. You can see this is changing to all sorts of patterns. That this is the 3D pattern that I'm talking about in 2D. So it takes a little bit of interpretation to actually do this. If we change the phase, just let me get something up that is slightly more recognizable. So we've got slightly more of the Q frequency, 50 Hertz more, and if we change the phase, you'll notice that circle, overlap circle, starts moving into each of the quadrants. So, and for when we talk about quadrature amplitude modulation, you'll notice that there is some sort of signal in each of those quadrants. For something like, quadrature amplitude modulation is used for digital television. You'll notice that there are a whole lot of dots that appear in the constellation diagram in each quadrant, and dependent on the number of dots is the number of what they call QAM. So it's 4, 16, 64 QAM, and that's how they represent it on a constellation diagram. Each of those areas are a particular representation. So now just let me go back here, because there was a good diagram. So this is, Warren, are you watching the the moon?
Yeah.
And making sure that the camera's on the moon?
I just checked, but it's clouded.
It's clouded over. Okay,
yeah.
all right. Because I'm keeping an eye on it here, but it hasn't appeared for quite a while. So.
Yeah, I'll check again shortly.
Okay, cool. Thank you. So, this is a good demonstration of we've got our phasor diagram here, our phasor diagram or our constellation diagram here. Now, as it says, the F and the F minus are the blue and the red that are constant amplitude, so they are heading around the circle at different rates because they're different frequencies. The green is the product of the complex signal, and the black is the product of the corresponding real signal. So what we're talking about here, the complex signal, which is the imaginary and the real signal, and the black is just the real signal. So if we then plot what's going on here on the phasor diagram in 2D, you can see that the red and the blue are slightly different frequencies, just slightly, or they'd be on top of each other, so they're just slightly different. The green is the product of the complex signals put together, and the black is the product of the real signal. And you'll notice the black is staying positive, and it is the same frequency. It's double the frequency, because it's the addition, it's the product of those, the blue and the red, and the green is just solid. It's staying at one level all the way through. Green is quite rightly 0. That's correct. That's correct. And the signal, the black signal, is 2 times the frequency. Now, slightly more complex. Now, this is fairly hard to see in the 2D, but you've got 3 frequencies all at 3 different frequencies, and then you've got your so the blue and the red, 10 kilohertz in red and 3 kilohertz in blue. We get the result of using I and Q in the green, so that's the combination of the blue and the red. And the black represents the real frequency that you actually get out. So this is a much more complex and harder. You can see the black is here, and there's some differences and phase changes and all sorts of stuff in there. But it is what I'm trying to get at here is I and Q. If you reduce your frequency, your amplitude, and your phase to an I and Q signal, so 2 numbers, you can literally represent anything in the frequency, amplitude and phase of that particular signal that you're trying to represent. Now, given that they're numbers, it's really easy to be able to actually process those numbers in a software-defined radio. So that's why we go to a lot of trouble of converting things to I and Q to actually see that to be able to then process them, take them through filters, do all sorts of things to them on the way through, and represent our frequency, our amplitude, and our phase, and any modulation that you actually want to do to that signal for that. So anyway, I hope I probably confused everybody totally on that one, but it's just the reason why we convert them to I and Q is it makes it so much easier to then do any sort of processing, either modulation or demodulation. It's just the reverse of it, or in a software-defined radio setting. So there you go. Now, I just wanted to finish off with now probably confused everybody in there, but anyway. Now, exercise 3 in our workshop. This is where we'll finish off with exercise 3 today, because I want to actually show this because we've seen most of these blocks already. Apart from, I've introduced, there is a noise source block, which is exactly that. It's a source of noise. You can adjust the amplitude. You can seed the block with a particular sequence if you would like to. If you leave it as 0, it's a random sequence. You can set the amplitude, and you can also set the type of noise. So let's see what types of noise we've got. Uniform noise. That would be nice, because then you can get rid of it. Gaussian noise, which we'll go into, we'll actually use that. Laplacian noise and impulse noise. So we'll leave it as Gaussian noise, and I'll show you what that actually looks like. We put that noise through a low pass filter. So this is a transformation block that I was talking about before. There's a few things here. You've got the ability to decimate. Now, all that decimation means in a software defined radio sense is you can decimate a particular signal so that you only take particular samples. So if I was to set that to, say, decimation rate of 10, it would take every 10th sample and only allow through that 10th sample, every 10th sample. Now, in a lot of cases with software defined radio, you can actually create and recreate a signal by actually, you don't need all of the samples of the signal to actually get the same result out the other end. And what this means is, from a processing point of view, is it can cut down the amount of processing that the digital signal processor or the CPU or whatever you're using actually does. So it can actually reduce the amount of load on the actual processing side of it. You also need to do some decimation to sometimes to meet Nyquist's law, which is the sample rate's got to be 2 times the frequency that you're sampling as a minimum. So you do need to do some of that, because you one of the things that GNU Radio Companion will complain about is if you actually set something up so that it goes against Nyquist's law. So sample rate, the sample rate is 32K, set by the variable sample rate up here, which is a default. The cutoff frequency I've set at 5,000, and I'll show you that in a minute, 5,000 Hertz. And the transition width, which is the increase and the decrease of that particular filter over 2,000 Hertz. The type is what we call Hamming, and there's some other options that are available to you: Han, Blackman, Rectangular, or Kaiser. Hamming is the one that we'll be using, and the beta, or the now what's that mean? I'm actually not sure what that means, because there's a gain control up here. Leave that one with me. I'll go into that next time. I'll take that on as a note. So that's the low pass filter settings that you can actually set up here. So we've set it up for cutoff frequency at 5K, a transition width of 2K. We've got a signal source here of 4K that we've set it to, an amplitude. We've got a throttle here because there's no external clocks available to us here. We add those two signals together and we come out on our frequency, our well-known frequency sync, which is our oscilloscope view of the world. So let's execute that particular flow graph, and you'll see that it has two components, one of which is the Gaussian noise. So this is the noise that you're seeing here, and surprise surprise, it is plus and minus 5 kilohertz. Now again, we've got negative frequency here because there's no concept of there being positive and negative, a difference between positive and negative. So it's the edges of that particular low pass filter are at 5, and the transition from this low to a high is over to 2 kilohertz. And this peak here, surprise surprise, is our 4 kilohertz signal. So that's showing us the noise source, the adding block, and the low pass filter. So it is only allowing through anything below 5 kilohertz. So let's take our low pass filter out. Now, as soon as I take that out, you'll notice the add block and the noise block goes red because there's nothing connected to it. We can just connect this up like that, because these two are the same, and everything goes black, which is fantastic. And we'll do an execution. And now, so we've got a Gaussian noise source, no low pass filter. Gaussian noise source at an amplitude of 100 M, and I don't actually know what 100 M is, but by the look of it, it's about minus 60 dB. so, and it's across the spectrum that we're actually dealing with here, which is plus and minus 15. So it gives you an idea about the low pass filter. Putting it in does give you that low pass function in both the positive and the negative frequencies, the positive and negative frequency spectrums, and you can set that pass. You can make it a low pass, you can make it a band pass, you can make it a high pass, whatever you need to do to actually process that particular signal on the way through. So just let me. Ooh. Oh. Looky. We have a bit of a moon.
HB9GWX connected.
Oh, HB9. Well, there you go. Here we go. Look at this. Love it. Oh, it's a camera outside. I don't think Warren's outside. And look, it is starting the eclipse. It is actually about half eclipsed. I love it. Well, there you go. Oh, that's cloud. I don't think so. If the cloud disappears, there's a bit of darkness on the moon. Ah, come on. No, it's gone. Okay, back to our Gaussian noise. We've got our outside broadcast set up there. Oh, hang on. I think that's a HB9. Does somebody... You want to talk to a HB9? Via that thing. I love it. Oh no, very good. Oh no, well it's happening. It's a happening thing. So there you go. This is real time television. So okay, that's our Gaussian noise. It is a transformational block, the low pass filter. You've got a noise source, you've got a signal source. We know about throttles, we know about adding together, and we know about the oscilloscope sync. We also know about the constellation sync that we used when I was demonstrating IQ. So we're using more and more blocks to actually... See you, Ken. Good to see you. Oh, okay. Oh, cool. Okay. Cool. Safe travels. Cheers. So we're starting to do some real things with GNU Radio Companion. I'll just give you a hint of what we're going to be doing next time. Slightly more complex, so we're getting more and more complex. We've got various signal sources. We've actually got a recording that we're going to be using. That can be an input, it can be a file source. We've got some tuning arrangements that we can do here. We've got a signal source. We multiply these together, go out to a frequency sync, which is what our oscillograph. But we also go out, and you'll notice we split here into two paths. So you can see here on certain things you can actually split into two. One goes out to an audio sync so we can listen to it, and one goes to the oscillograph so that we can actually look at it. So that's our next one for in a fortnight's time. So let's go back to here and just keep an eye on... Oh, look at that. that's pretty impressive. We've got an aerial wire right across the moon right at the moment. So Murphy's Law.
Spiderweb.
Yes. So, but it looks as if the cloud might be clearing enough for when, in fact, there's a good. Oh no, not cloud. Go away. Anyway, okay. So next time we will be doing exercise 4, which is lots more blocks, and it's using also the key thing here is it demonstrates using a file source. I will be getting to, in some of the other the further on exercises, I will be using an RTL SDR as a signal source, so real application type stuff. So we'll get to that, but we really needed to build up how to use the tool, what you do in the tool, what it means in the tool, how to configure the tool, because there is just so much you can do in this tool. It is just phenomenal. It's a fantastic toolbox, and there is the GNU Radio channel on YouTube worth a look, because there are regular amateur radio run by amateurs on the use of GNU Radio Companion to do a whole lot of things in amateur radio. Well worth a look. They get together virtually quite often, and they record those sessions and make them available on the YouTube channel. So really, really good. So next time, a little bit about exercise 4. Also, we're going to have a look at the filter designer. There is a really nice filter designer that comes with GNU Radio. So if you want to actually build your own filter and then make it a module, this is how you do it. And also a little bit around more around modifying blocks and the way that you actually do it. So that's on June the 9th, because next week is our presentation night, which is Mike Hawkins, VK7DMH, on satellites and satellite antennas, and we'll actually he came up tonight and tested everything out, and it seems to all be working, so which is really good. So that'll be next week. It will be on the YouTube streaming channel, so you will be able to watch that remotely, or you can come up to the COVID safe club rooms and watch it in person and be able to ask Mike in person. So that's June the 2nd. Now our August presentation night is contesting with VK7 Martin, VK7GN on HF, and our very own Martin and our very own Richard on VHF and above contesting. And then September the 1st is our Tas Government Radio Network presentation with Andrew VK7AJ. So just have July in there that we're trying to fill in right at the moment, but we'll get there. So now, any questions or comments from our viewers? Any questions or comments? Now, just while that's coming through, videos for our RF viewers. Next weekend, this coming weekend, is the 2nd annual YouTube Hamfest for 2021. Ham Radio DX, so Hayden VK7HH is participating in that. We got a little bit of a promo video of that as our first video for our RF viewers. Then we've got W2AEW Alan, who gives a fantastic explanation of I and Q. Got some great little diagrams that he draws. Part 1 and Part 2. So he has a fantastic way of explaining things in a very easy and easy to understand way. And then we finish off with another one of the Vertasium videos, which is how an infinite hotel ran out of rooms, which is a fascinating little discussion on infinity and the different types of infinity. And if you thought there was only one type of infinity, I think this particular video might prove you wrong. So anyway, that's our presentation night for tonight. Hope you got something out of it. A little bit more on GNU Radio Companion, and hopefully you've got a little bit more understanding of I and Q signals. And look at this, on Q we've got the moon breaking through from our outside broadcast camera for the blood moon, the big blood moon. Sounds like a Hammer House of Horror episode, but it certainly isn't. That's our blood moon that we're watching as we speak. So this is VK7 Tango Whiskey for VK7 Oscar Tango Charlie OTC, the club station of the Radio and Electronics Association of Southern Tasmania, with our DATV Experimenters Night, and we'll catch you next time. 73.